We've previously looked at two independent bodies. In our very first video, we looked at the three different types: two independent bodies, body and carrier, and wind appears. We've looked at the first type and broken it down into parts. The last two types aren't near as long as the first type, so we're going to take a look at the body and carrier ones for this lesson. So body and carrier, what we're talking about there is that if we have a body of a plane, the carrier is going to be the wind. If we have a body of a boat, the carrier is going to be the river or the current. So that's what we're talking about, body and carrier. You'll either have a boat in water and it'll be going probably from one side of a river to another, or you'll have a plane going from one place to another, and then we're talking about how the wind or the current is going to affect it. So things that we need to do for this: we always need to draw a diagram. We'll need three things for the diagram. We need the velocity of the body, the velocity of the carrier, and the velocity of the body relative to the carrier. Make sure you don't mix up velocity and position, and if you need to, you can use separate diagrams. And if you're looking for an angle for velocity, you can use position diagrams to help you find velocity angles. Okay, so things to watch out for with this one then. Terms for velocity of body relative to carrier. The ways that this can be asked is just the very basic one of velocity of body relative to carrier, which you would know. The velocity of body in still air or in still water. That's also VBC, okay? So just be aware of that. Or velocity at which it starts before current or wind takes it. So make sure that if you see these, that you know you now have the velocity of body relative to carrier. Then for terms to watch out for the velocity of the body is, again, velocity of body, which you would know. Final or actual velocity of body. Velocity of body is observed from the ground, if that's a plane. Velocity of body after carrier is taken into account. So they're ones, again, that we need to watch out for. They'll use those phrases in questions and we'll have to know what they're talking about. Okay, two things then to remember for this body and carrier type are these two headings here, these two words. To cross quickly. If the question says that they want to cross the river as quick as possible, we need to head straight. So we need to we're going to end up heading straight. The current is going to take us a little bit downstream and we're going to go across as quickly as possible. To cross using the shortest distance, then what we're going to have to do is we're going to have to end up going upstream a little bit into the current, and then the current is going to take us and we're going to end up directly across, or as close to directly across as possible. So they're the two ones to watch out for. To cross quickly, you're heading straight, and to cross using the shortest distance, you're heading upstream at an angle, and then you're going to try and end up as directly across from your starting position as possible. Let's take a look at a question here. So this one here, it says a boat can travel at 13 meters per second in still water. So that was something that we had mentioned earlier, this in still water. That means that's VBC, so the velocity of body relative to carrier. It has to travel across a stream which is 78 meters wide and flowing at 5 meters per second parallel to the bank. How long will the crossing take if we go by the quickest route? So let's look at that first question there. We're going to go by the quickest route. So we know that if we're going by the quickest route, we need to head straight across and we're going to end up slightly downstream. So what I'm going to do is I'm always going to draw out my graph. So that's the first step, draw out your graph. If you need to draw a position one separately, you can, but I'm going to just say this is my 78 meters. And I know that this is my starting position in my boat. And I want to get across the river. But I know that the flow of the river is going downstream at 5 meters per second. And I know that the boat can travel at 13 meters per second in still water. So we need to get across. So what's going to happen here is that for every 13 meters that I travel, the river is going to take me 5 meters downstream. So what I'm going to do there is you're going to end up drawing then, this is your position graph, and then you can draw on top of it your other graph if it's something basic like this question here. And we can say if we're going to go across as quickly as possible, that means that I'm going to try and go straight across. So what's going to happen here is I'm going to go across 13 meters per second. And then what happens is the river is going to end up taking me 5 meters per second downstream. And that's going to happen over and over again until I reach the other side, the 78 whole meters. So what we're doing for this question, because we know we're going straight across 13 meters, I'm going to just take my distance, speed and time triangle, and I am going to look for time. So that's going to be distance over speed. So time is distance over speed because they're looking for how long. So time is going to be my distance, which is 78. I know I'm going 13 meters per second straight across because I want to head straight across. So that means that I'm going to end up taking 6 seconds to do so. Okay, now bear in mind that I'm not going to land here. I'm going to land down here somewhere. And if you were asked for where you landed in that case, what you can do is you can say, okay, well, I'm going to keep going that way. And for every 13 meters, every one of these I do, I'm going to do one of these. So I know if it takes me 6 seconds, it takes me this 6 times. So I could say 5 times 6 gives me 30. So I know I end up 30 meters down this way. So if I go to look at the second part of this question then, it asks us for the shortest distance. So the shortest distance, what you end up doing here is you want to end up making this line here. Because we have a right angled triangle, we're always going to either have this in still water bit, either going to be one of the sides or it's going to be the hypotenuse. If you want it to be the hypotenuse, we'll draw our graph out again. I know it's going to be 78 meters. And I know my 13 meters now, what I'm going to do is I'm going to try and aim to end up over here if I can. And I'm going to go up this way. Now I don't know at what angle I'll go, but I'll know I'll go 13 meters per second. And what happens with that 13 meters per second is that I'm pulled back 5 meters. So I know then that if I use Pythagoras, I can find this here. And there's my right angle triangle. And I'm going to find out what that green line is worth. Okay, so I have 12 squared minus 5 squared equals that x squared. So I'm going to get the square root of that equals x. And that gives me 12 equals x. And that's meters per second. So I know that this is now 12 meters per second. So what I'm going to do here is I'm going to use my distance, speed and time again. And for my distance, speed and time, I'm looking for time is equal to distance over speed. So that's going to be my distance is 78 over my speed of, that's now going straight across, the 12. So that gives me 6.5 seconds. So just a little something to be aware of here. For the questions that we're going to look at now, all of them have the ability to create a right angled triangle. If you come across a question where the river is flowing faster than you're able to swim or the boat is able to move, then that means that you don't have a right angle triangle. You'll end up with some kind of triangle. You'll be going across this way, it'll go down that way, and you'll end up with a triangle like that. And that brings in what's called the sine rule and the cos rule into it, or the cosine rule into it. So we'll look at that a little bit later on, but for the moment we're just going to work with the right angle triangles where our boat can travel faster than our water is flowing.